Good evening, everyone. Welcome to the week 6 of the course problem solving session of the course Matrix Analysis and Application, NOC 23 MA91. I am Pawan Raikwade. I will be explaining some sample problems here that will help you understand the concept better and solve the assignments by your own. So let's get started. Can anyone confirm if I am audible and also the screen is visible?
Yes.
Yes, sir.
Okay, thank you. So we have question number 1. So paragraph 1 says that we have to use the matrix A, this matrix, for the questions 1 to 3. Regarding the doubts that you asked in last week, I'm so sorry, in this week I couldn't get much time to look on those. I will definitely go for it on next week. I'm sorry for this week. Okay.
Okay, sir.
Okay. So let's solve these questions together. You have a matrix A. Question number 1 asks, what are the generalized eigenvectors of A? Basically. So they have given just two, but so in this case, generalized eigenvector. What is a generalized eigenvector? First thing is the definition of an eigenvector. You say X is an eigenvector corresponding to eigenvalue lambda if you have Ax equals to lambda x, right? So X has to be non-zero. But I can rewrite this as Ax minus lambda x at 0, which implies A minus lambda I at x is 0, which implies, see from there, x belongs to null space of A minus lambda I, right? Even this is the thing enough. So we are going to replace this condition here, by the power, maybe R. If this is going to happen, then we'll say X is a generalized eigenvector. Okay, this is the definition corresponding to any eigenvalue lambda. We call X as a generalized eigenvector if satisfies this equation. Equation star. For if R equals to 1, then generalized eigenvector is itself an eigenvector. Okay. So, in fact, there is some ambiguity in this question because whenever you say generalized eigenvectors, you also count eigenvectors in that. So there has to be, I don't know, possibly 3 eigenvectors, but still they have, in all the options there are just 2. Okay, let's see. Okay, we have A as 2, 2, 1, 0, 3, 1, 0, minus 1, 1. In order to find generalized eigenvectors, the first step is to find eigenvalues, right? Only after finding eigenvalues, you can find the eigenvectors. So what can be the eigenvalue? Can anyone find?
Sir, by seeing first column of this matrix, 2 is the eigenvalue.
Perfect, yeah. 2 is an eigenvalue. Corresponding eigenvector is E1.
Now
So what?
we can use the trace and determinant of the matrix.
Perfect, perfect. So now the eigenvalues are, let's say, 2 plus lambda 1 plus lambda 2 is the trace, which is 6, and 2 times lambda 1, lambda 2 is the determinant. What is the determinant? 2 times 3 minus plus 1. Yeah, that's enough, because if I count determinant in this direction, all others are 0. So this is 8. So product. Is my calculations correct? Please verify.
Yes, sir.
Yes, sir.
So lambda 1 into lambda 2, I'll get as 4. And this. So quickly, can anyone tell me what will be the lambda 1 and lambda 2? The sum is 4, product is 4, of course, 2. So all eigenvalues are 2. Okay, we have to find generalized eigenvectors. See, for eigenvectors, we don't know how many eigenvectors will be there, right? It depends on geometric multiplicity, right? Number of linearly independent eigenvectors corresponding to an eigenvalue is its geometric multiplicity. But for generalized eigenvectors, it says that you have um, algebraic multiplicity number of generalized eigenvector always. Okay, for example, here the algebraic multiplicity of 2 is 3, right? Which implies you will have 3 linearly independent generalized eigenvectors. Let's find those. So the first one is x1, which is E1 simply, is 1 0 0, right? So now to find another eigenvector x2, what I have to solve, maybe x minus a minus lambda I, I'll say squared, right? Times x has to be 0, correct? So I have to find, does this equation has a solution or not? But if you see, what is a minus lambda I squared x? It is a minus lambda I, right? Correct? That means now this vector, if I call this vector as, let's say, x1, no, not x1, maybe y. So if x satisfies equation 1, then y becomes an eigenvector, right? But the only okay, we have to first find what is the geometric multiplicity of this matrix. Sorry, of this eigenvalue 2. Let's see, a minus 2I, 0 to 1, 0 to 1, then 0 1 1, then 0 minus 1 minus 1. Okay, so what is the rank? It's 2, implies geometric multiplicity of eigenvalue 2 is 1. Am I correct? Geometric
Yes,
multiplicity
sir.
of 2 will be nullity of a minus 2I, which will be 3 minus rank, which is 1. That means you
Yes.
will have only one linearly independent eigenvector, right? So now if y is an eigenvector, what do you have? You have y itself with some alpha times x1, right? The x1 that you choose, this guy, correct? That means if I want to find an x such that a minus lambda I square x equals to 0, I have to find that x should satisfy this equation a minus lambda I x is equals to x1. Do you get this point? I'll repeat again. If x satisfies equation 1, that implies a minus lambda I squared x is 0. From here we get here. That implies a minus lambda I at x, if I name it as y, this guy, if I name it as y, then y is an eigenvector corresponding to eigenvalue 2. But as we know, there is only one eigenvector corresponding to eigenvalue 2, which is this x1, right? Hence we get a minus lambda I x equals to x1. So I need to solve this equation in order to solve equation number 1. That's equivalent. So let's see if there exists a solution for this. I'll call this as equation number 2. Now a minus 2I. Just replace 2 here. 0, 2, 1, 0, 1, 1, 0, minus 1, minus 1. At x1 is 1, 0, 0. Do we have a solution for this? Just a minute. Yeah. So now we have to find whether equation 2 has a solution or not. Let's see. Equivalent is equivalent to 1/3 R3. I'll do R3 changes to R3 plus R2. So I'll get 0, 0 here. Is 0, 0. It must have a solution. In fact, infinitely many solutions.
Yes, 0, 1, minus 1.
Okay, perfect. So you find, I'll name this as x2, 0, 1, minus 1.
1 minus 1.
Yeah, perfect. That's the solution. Yes. So I get x2 such that a minus lambda I x2 is x1, right? What happens? I'll go in the reverse direction now. Now what if I apply a minus lambda I again on this guy? Or if I do this, a minus lambda squared x2 is a minus lambda I times a minus lambda I x2, but I know a minus lambda I x2 is equals to x1, and since x1 is an eigenvector, forgive me for writing lambda always, we know what lambda is here, it is 2, but we know that x1 is an eigenvector, hence this is 0, which implies x2 is an eigenvector, sorry, generalized eigenvector. Now similarly, let's go for 3. Yeah, but wait for this. How many linearly independent we can get from this equation number 2?
So
Yeah, just a minute, someone wait. Yeah, so
one
from, sorry,
GM of 2, sir, equals to 1 Li eigenvector.
yeah, we got just one eigenvector, right? Linearly independent from this equation, generalized eigenvector. Yeah, if I want to solve really this equation here, I'll get, let's say, where to write. I get 2, x2 is confusing now because I named those as vectors. So I'll write like alpha something. 2 alpha 2 plus alpha 3 should be 1. And then I get alpha 2 plus alpha 3 should be 0. So that means alpha 2 has to be minus alpha 3. Alpha 1 can be anything. But Something is wrong. Oh, sorry. You have alpha 2 equals to alpha minus alpha 3 from here. If you put it there, you get 2 alpha 2 plus, let's say, alpha 3 as minus alpha 2. You have 1. Implies you get alpha 2 as 1 and alpha 3 as minus 1. Ah, okay. So the only choice we have is for alpha 1. Can be anything. Yeah. And we choose that alpha 1 to be 0. Right? 0, 1, minus 1. As you can see, alpha 2 is 1, alpha 3 is minus 1. Okay. So you get at most one generalized linearly independent eigenvector when you say a minus lambda squared is 0. Now let's go for r equals to 3. That is a minus lambda I cube at x equals to 0. Now we want to solve this equation. But similar to the previous process, if I want to solve this, it's equivalent to solving, right? Because x2 is the solution for the system a minus lambda I squared x equals to 0, right? Hence, if a minus lambda I squared of this vector is 0, then this has to be equals to x2. Is it clear? This is the same procedure that we did for the squares. We're doing it for cube. Now,
Not understanding, sir.
this step we didn't understand. Did you
Sir, can
understood
you
for?
show options? Options.
Yes. Here are the options. Hmm. At least we have one vector here that suits our two vectors here and here, the first vector. Let's find out the other eigenvector and then we can match the options. Okay, I'll repeat again the procedure that I am doing. I want to solve a minus lambda I cube x equals to 0. That is equivalent to solving. I pull this squared outside and then this one bracket inside. Right? I wrote it here. That means if I call this a minus lambda x as y, then this equation is just a minus lambda I squared y equals to 0. Right? But we have just solved this equation. Equation number 1, a minus lambda I squared x equals to 0. What is the solution for this equation? Here, any vector of this form, alpha 1 minus 1, right?
Yes, sir.
Yes. So in particular, because in options we have the first coordinate as 1 everywhere, we chose here 0. In place of 0, we'll choose 1 here. Doesn't matter, right? Hence, we are going to solve this equation that a minus lambda I x equals to x2. x2 is 1, 1, minus 1. Okay. Even 0, 1, minus 1 works. No problem. But in the option, there is no 0, 1, minus 1. Hence, I chose 1, 1, minus 1. Okay, I hope this x2 we haven't used anywhere yet. Yeah. Now we have to solve this equation number 2. What is a minus 2I again? 0, 2, 1, 0, 1. 1 is this. Is it? No, minus 1, minus 1. The right side vector is this. So again do the same procedure. R3 plus R2. There exists a solution with conditions as which implies if I solve these two, get 2 minus 2 is 0. 3 minus 2 alpha 3 is minus alpha 3 minus 1. So implies alpha 3 is 1 and alpha 2 is 0. I think that will work. And alpha 1 can be anything.
101.
Yeah? Oh, sorry, hello?
Alpha 1, we can take 1.
Alpha 1, yeah, alpha 1 we can take anything.
Okay.
So, yeah, the solution we have right now, I'll call the solution as x3 is, I'll call alpha 3, I'll take alpha 1 as 1 for consistency.
101.
Yeah, and then alpha 2 will be 0 and then alpha 3 will be 1. Is the eigenvectors we got, generalized eigenvectors. The first one was the eigenvector 1 0 0. Second one we got as 1 1 minus 1, if I remember correct. Third one we just now got as 1 0 1. So these are the three eigenvectors, linearly independent eigenvectors. So let's see the match. So you have 1 1 minus 1 and 1 0 1, the option number 1. Do you understand the whole procedure? Is there any doubt? Yes, Suraj Pathak, you open the hand. Do you have any doubt?
What difference between eigenvector versus generalized eigenvector?
What? Can you repeat?
Eigenvector versus generalized eigenvector.
What is the difference?
Yes, yes.
Yeah, okay, I'll repeat. I just said it in the start. Eigenvector, if and only if you have this condition, ax should be same as lambda x, right? Or equivalently, you should have a minus lambda I x should be 0, right? Here you can see the coefficient is 1, kind of, a minus lambda raised to 1. But for generalized eigenvector, this condition need not hold, but what holds is a minus lambda raised to power r for some r, x is 0. So kind of you can say that x is an eigenvector for the matrix a minus lambda raised to r. Okay, or that's just complicated. Don't think about it. Okay, so here you have a minus lambda I x 0, but in generalized eigenvector, the r will come up. Yeah. For example, in the current matrix that we took, what was it? 2, 2, 1, then uh, 2, 2, 1, 0, 3, 1, 0, minus 1. In this matrix, you can see the vector 1, 0, 0 as an eigenvector because if you compute a 1, 0, 0, you get 2 times 1, 0, 0. But the other vector that we choose as a generalized eigenvector 1, 1 minus 1, if I compute a 1, 1 minus 1, what will I get? 1, 1 minus 1, 2, 2, 4 minus 1, 3, 3 minus 1, 2, 3, see, minus 3, 2, 0. This is no longer an eigenvector. Sorry, see, because ax is not same as 2 times x, right? So that's the difference. But if I compute a minus 2I raised squared, what will it be? A minus 2I will be 0, 2, 1, then 0, 1, 1, 0 minus 1 minus 1 squared. If I do this, the square first column will be as it is, then 2, 1 minus 1. So 2 minus 1 is plus 1, minus 0, minus 1 is 0, then 1, 1 minus 1. Same thing. I hope I'm correct. Yeah. This is a minus 2I squared. Okay. Now if you plug in this vector this vector here, what will you get? You get 1, 1 minus 0. See? This is the difference between generalized eigenvector. A minus 2i squared at x is 0, but a minus 2i at x is non-zero. Do you see the difference now?
sir, इसमें geometric multiplicity we take this process. Geometric for finding geometric multiplicity we take this process.
No. For finding geometric multiplicity, you just find the nullity of this matrix A minus lambda I. You find the nullity, or you can find the rank of this matrix A minus lambda I, and then this nullity will be n minus rank, whatever it is. This is not a
Okay,
process to find nullity. This is to find generalized eigenvectors.
okay.
Okay. I hope this is clear.
Sir,
Yes.
so here R is starting from 2 in generalized eigenvector.
No, it can start. You see, I told before also, even for r equals to 1, it is eigenvector, and every eigenvector is a generalized eigenvector. No issue of calling that as a generalized eigenvector.
Okay, sir.
R can be anything in natural numbers. Okay, it can be 1, it can be 2, 3, 4, anything.
Okay, sir.
Yeah. But if you want to really separate eigenvectors and generalized eigenvectors, then you can say R has to be greater or equal to. By the name only, we suggest, right? It is generalizing the eigenvector property. The eigenvector property is being the null space of A minus lambda I. And the generalization of this is being in the null space of A minus lambda I raised to R for some R. If R is 1, then this is the same, but if R goes higher, that's more general. Okay, so now we want to,
Hello, sir.
yes?
How we fix R? How we can determine R so that we can get the general diagnosis for any matrix?
Yeah, so I think R will lie between 1 through n always.
Okay, thank
Yeah, yeah. If lambda is an eigenvalue, you can always find an x such that A minus lambda I raised to R equals to 0 for R in between 1 through n. Okay, so you can just check for each R maybe, and then you can find.
you. Okay, sir, you can proceed.
So now we have to calculate A raised to 4, this matrix, which is a very dumb question, because the more naturally you can just do the multiplication and find A raised to 4. But what they want us to test is, you know that by generalized eigenvectors, you can write a Jordan canonical form for a matrix A with PJP inverse, right? Where this P matrix consists of generalized eigenvectors as columns. And J is the Jordan form, Jordan form. It will be like consisting of Jordan blocks. This is one block, and for another eigenvalue you have the block. Right? I hope this Jordan block has been explained in the lecture videos. It is, right?
Yes.
Yeah, okay, good. So once you have a Jordan decomposition, what do you know is a power, if I do the square now, what I'll get? Right? This is a, this is a. This middle term gets cancelled. Right? So from this you can say a power n for a natural number n is just p times j power n p inverse. That's all. So now you have you can write the matrix A as simply the P that we just found out, the first vector has 1, 0, 0, second has maybe 1, 1, -1, third was what, 1, 0, 1. Yes. Then the Jordan form, only eigenvalues are 2, so this is the Jordan form, and then its inverse. Please calculate whatever it is. And then A raised to 4 will be the same matrix here, and this matrix raised to 4. Okay, and then this is P inverse. Okay, please do the calculation. This is just the calculation stuff now. You have to the only ease that you got after doing this Jordan canonical form is the ease in finding J raised to 4. There is some formula to find the exponents of Jordan blocks, something related to this entries. You can either do directly J raised to 4, or you can use the formula and find the J raised to 4. Okay, I hope this is I can leave this as an exercise. You can compute this product. Is there any doubt in this?
No, sir.
No, sir.
Oh, okay. Let's go for the next. The minimal polynomial of A is. See, first one I can decline directly. Can anyone give me the reason?
Because x minus 2
Because
whole cube
the
is the
eigenvalue.
correct
Yeah. But
polynomial.
yeah, but that doesn't answer my question. Why can I
Sir,
decline option number one?
Irreducible.
zero,
Zero is not eigenvalue.
Yes,
zero
perfect.
is not eigenvalue.
Perfect. That's the answer. Yeah, x minus 2 cube is the right answer. But for first instance, you don't know, right? What's the answer? I don't know how you come up with that. But I can decline it just by saying, because every zero of the minimal polynomial is an eigenvalue of the matrix. But as we have just seen that only eigenvalue of A is 2. Hence, first option is the wrong option. Okay. Now, what I know is the degree of the factor x minus lambda in minimal polynomial is the size of largest Jordan block, right? I mean, when I consider the Jordan decomposition of a matrix A, then whatever, I mean, corresponding to eigenvalue lambda, whatever is the maximum Jordan block corresponding to eigenvalue lambda, that will be the degree of x minus lambda in minimal polynomial. We have just seen the Jordan decomposition. Here, there is only one block, two, because geometric multiplicity is 1, and that is equal to number of Jordan blocks. What is the size of this block? 3, right?
Three.
Yes, hence this is the right answer. Maybe I can also write the note here. Number of Jordan blocks is equals to what do you say, geometric corresponding to eigenvalue lambda is same as geometric multiplicity of eigenvalue lambda, which is same as nullity of the matrix A minus lambda I, which is same as rank n minus rank of A minus lambda I, but okay, I don't write that. Let's go to question number 4. Okay, same the matrix formulas. What we'll do first is, in order to find A raised to A, we'll find Jordan form, and then E raised to A is just, as far as I remember, right? Is this correct? Or there is some exponential of P involved as well?
Sir, first identity is come.
Where? Okay, we already have a Jordan block, is it? Oh, we already have a Jordan block. A
Sir,
matrix
this
is
is
a
equal
Jordan
to him.
block. So the question is, what is e power a, right? Okay. So basically, we'll go by the series expansion, right? The whole formula is derived by series expansion. We'll see how it is. The e raised to x series is 1 plus x squared by 2 factorial plus x cubed by 3 factorial, right? In this way, we'll proceed. So when I do a matrix, I can just put it as it is, but in place of 1, I get identity, then I get a, then I get a squared by 2 factorial, and I'm like this. So I just have to see the pattern in these a squares and all, right? So if I have a Jordan block, say lambda, 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 let's just see for 3 cross 3, what's happening. What will be j squared? It will be lambda squared 0, 0, then okay, then lambda plus lambda. This is 0, this is 1. Okay, also do the computation so that I won't be wrong. Here is lambda squared. Here I get lambda plus lambda. Then I get here lambda squared. Okay, this is lambda squared. What is j cube? I'll just write it. Okay, so this is lambda cube, lambda cube, lambda cube. Here now I have lambda squared.
Sir, option D is
Option D. I mean, I don't know the answer, but can you help me getting to the answer? I don't know how you get to the answer. Okay, so as far as I can see, lambda squared plus 2 lambda squared. And here I get the third. Okay, in the third I get 0, 2 lambda plus lambda, 3 lambda.
Sir, there is a formula explained by already sir in video lecture.
Can you please tell me that formula for j raised to n? I
Just a
don't know.
second, just a second.
Yes. I'm calculating the formula right now.
sir, in first row, e to the
Yeah.
power lambda, e to the power lambda, e to the power lambda upon factorial 2, and
No, no,
so
no.
on
You're saying for e power j or you're saying for j raised to n?
e to the power j.
E power j, you're saying, okay. So yeah, the diagonals, I expect it to be e power lambda,
Yes,
or no? Is it? What is it?
sir. If there is k by k, then first row e to the power lambda, next element a1 to e to the power lambda, and e to the power lambda upon factorial 2, and last one e to the power lambda upon factorial k minus 1. So because our Jordan block is 3 cross 3,
Hmm.
and then 3 is 1 cross 1.
Hmm.
So according to Jordan blocks, first 3 cross 3 e to the power lambda, that is e to the power 2, e to the power 2, and then e to the power 2 upon factorial 2, that is 2.
Okay.
And then in second row 0, e to the power lambda, e to the power lambda.
Okay, just give me a minute. It's hard to follow up by just listening. Give me a minute. I may be looking for the actual formula if I get a formula. And there is a direct formula. In fact, you don't have to worry much. I was trying to derive that formula because you can see if I
Yes.
want to add this up, I didn't what will be the first column in the whole summation, the first entry. Identity's first entry is 1, then I'll get j's first entry which is lambda, then I get j square second entry which is lambda squared upon 2 factorial from this. Then the third entry, first entry of j cube will be lambda cube upon 3 factorial from this. So this turns out to be e power lambda, right?
Yes.
That's how you get e power lambda here,
Lambda.
here, and here everywhere. I was calculating the formula for the other entries, but okay, I think that will take time. We'll just look at the formulas. Yes, someone raised their hand. Is there any problem?
Sir, second entry is also e raised to lambda.
Is it?
E raised to lambda. Second entry in first row.
Are you sure? Because
Yes, sir. It is explained by sir, and this is
okay.
given to us in formula and also in notes.
Oh, that's cool. That's cool. Just give me a minute. I'm looking for it. Okay, so what you are saying is if my j is let's say lambda just for 3 cross 3 case suppose or 4 curve. Okay. Then e power j you're saying as e power lambda, e power lambda, e power lambda 0 0 0. Here also e power lambda, here also e power lambda, and here.
E raised to lambda by 2 factorial. Yeah.
So that's how it goes. Okay. Oh, that's good.
Yes, sir. Yes, sir.
That's good. So now in here, okay, we have just a 3 cross 3 block here, and you have a single block here. So with that formula, e power a will be e power a for this e squared, e squared, e squared, e squared, e squared, and then e squared by 2 e squared, e cube. So is that correct?
Yes.
Yes, sir.
Yes.
Then option
Okay.
D, is it? Yes. Okay. Oh, that's good. Thank you. Thank you for the formula. Now let's go to question number 5. This was completely a formula-based question. Now we have to find singular values of this matrix. Okay. Can anyone tell me what are the singular values? What do you mean by singular value?
Maybe eigenvalues.
What?
Eigenvalues maybe.
No. Then why do you need a different name if they are the same? Eigenvalues, they are correct, but of what matrix? You're right. You're partially right. Singular values of A are basically are eigenvalues of the matrix A star A, or in the real case A transpose A. So for finding singular values of the matrix A, you just have to find what are the eigenvalues of A star A. So let's do the computations. A transpose A 050 minus 2302, then 20 root 3, then the matrix A.
Sir, can you take next one? We will do this one. No issue,
Perfect.
sir.
Perfect. This is just the calculation. You just have to find the eigenvalues. Yeah.
Yes. Yes. Sure.
Good. Thank you. Next one is let A be. Okay. Let's maybe give us some thoughts in just thinking. Is there any smarter way to find eigenvalues, singular values? If we know something other than this, hmm, because I am also attempting the question just now, so does anyone know any other smarter way? Because this kind of questions, I mean, this kind of question won't be there in uh, exams, CSIR and all those. But and does anyone know any smarter way to find singular values of such a matrix? Yeah, for the moment, even I don't know. So let's just go. Okay, let A be n cross n matrix and sigma max and lambda max denote the maximum singular and eigenvalue of a matrix. Then which of the following is true? Okay. Okay, let's see. The whole singular values, finding singular values is related to the singular value representation, or I'll say singular value decomposition. What it says is, if you find singular values, let's say sigma 1, sigma 2 until sigma n are singular values, and you can write those singular values in the diagonal matrix S, let's say. This is a diagonal matrix, and this is a representation to write a diagonal matrix. Then there exist unitary or maybe in real case orthogonal matrices. We'll say unitary. U comma V such that A is equals to U S V transpose. Okay, this is a singular value decomposition. And what's special is about the unitary matrices or the orthogonal matrices is that they preserve distance. Okay, they preserve distance. That is, norm of Ux will be same as norm X for all X, Cn or Rn, whatever it is. Okay, so unitary matrices or orthogonal matrices are the ones who preserve norm. Okay, now what I will have is, if I take any vector X for any X belongs to whatever the space is, norm of Ax will be same as norm of U S V transpose X, right? When I write A as this decomposition, I get this. You consider this as norm of U at this vector. Because U is a unitary, this norm is same as this, correct? But now S is just a diagonal matrix consisting of diagonal sigma 1 through sigma n, which are all greater or equal to 0. Hence, this quantity is less equal sigma max, right? Sigma max of norm V transpose X, right? This is a multiplication number, right? But now, because V is again unitary, this norm is same as norm X. What do you get? You started from norm AX is same as norm X, right? This is you got. Now, if suppose let's say let lambda be an eigenvalue, then Ax, I mean for some x, of course x is an eigenvector, then Ax equals to lambda x, right? Which implies what is norm Ax? Mod lambda norm x. But from equation 1, or I'll say equation 2 here, mod lambda, mod lambda norm x, this equals sigma max norm x. This is happening for every lambda, hence in particular lambda max. Do we have such an option? Sigma max, yeah. Yes. So is the solution clear? Do you have any doubts?
No, sir.
Good. Yeah, there this question was somewhat involved. The important property that you should have observed is norm of ux equals to norm x for every x if u is orthogonal matrices. Like, can anyone tell me proof for this? I mean, if u is orthogonal, then norm of ux, or maybe let's say square, the same as norm x square. These are called norm preserving operators. Can anyone tell me proof, or at least idea of the proof?
Norm ux square equal to inner product ux, then it is equal to inner product x u star ux.
Yes. Yes, perfect, perfect. So now because u is unitary, you know this is identity. Yes. Okay. That was a very short, quick proof. Thank you. We have used this property and the definition of singular value decomposition to solve question number 6. Okay, so now we have a question number 7, and now onwards we have a different matrix. A be a 3 cross 2 matrix with the singular value decomposition as this. This is U, this is V, this is S, sorry, this is S, and this is V. Okay, in this case, A is not a square matrix, so S will going to be a square matrix as well. Now you have to find the pseudo inverse of A. Okay, now in pseudo inverse is a Moore-Penrose inverse in this case. There are several types of pseudo inverses. The one that is there in the course is Moore-Penrose inverse. So the formula for Moore-Penrose inverse is whenever you have A equals to U S V star, and transpose in this case, then A dagger, the Moore-Penrose inverse, is V S dagger U star or U transpose. That's all. And what S dagger is, because S will be in this form somehow partial diagonal, right? Either diagonal in the rows or diagonal in the columns somehow. Then you just invert those entries, the diagonal entries, and that will be your S dagger, right? So you just have to do this computation. You take this as V, take this as U, take this as S, and you're done for finding the pseudo inverse. I'll skip this for the moment because that's just calculations. You can do it. Okay, then you have to find the non-trivial solution of A transpose X equals to 0. A transpose. First of all, A transpose will be V S transpose, then U. And if I plug in X to be 0, right? This has to be 0. But being unitary or orthogonal, V does not have any non-zero vector. As I mean, see, if A transpose X is 0, then you need this applied to V should be 0. But V is orthogonal, which implies its null space is 0. That implies S transpose UX has to be 0. Right? Sorry, S transpose UX has to be 0, correct. Okay, now what? Now S transpose is 2, 0, 0, 1, then 0, 0. So a vector y, let's say call this as y. And what do you want? You want to solve S transpose y equals to 0. What condition should you have? Y has to be in like E3 kind of thing, right? Because E3 is the only eigenvector. See, if you solve this, what do you get? You get 2y1 has to be 0, then y2 has to be 0, right? The only free variable is y3, which implies y has to be 0, 0, and y3. So like kind of belongs to span E3, third column vector. So that means you just have to solve ux equals to E3. Do you get the point? So ultimately, what the conclusion is, A transpose X equals to 0 if and only if Ux equals to E3, kind of, not equals to some alpha times E3, scalar multiple. So now we have reduced the question from A transpose X equals to 0 to Ux equals to alpha E3. Yes.
Sir, why S transpose UX is 0?
Why A transpose X is 0?
No, sir. S transpose UX, that will be used in your group. That's why.
Here, this step you're saying, right?
Yes, sir.
Yeah, see, A transpose X equals to what? V at S transpose Ux, right? Because A equals to V S transpose U.
Yes, sir.
So now, because V is orthogonal, it cannot have a non-zero vector such that Vx is 0 or Vy is 0, right? So if I boil down, okay, I'll rephrase the statement. If I say a matrix, let's say the name I'll call P, matrix P, um, how to say this, is invertible. See, every orthogonal matrix is invertible, right? If I say P is invertible and P y is 0, then what will you conclude about y? If I say the matrix P is invertible and Py is 0, then what can you say about y?
Y can be non-zero also.
Y can be non-zero. Can you repeat again?
No, okay, 0 is the only solution, sir.
Yeah,
Rank is full, then 0 is the only solution.
yeah, that's it. So the same thing applies here because V is invertible. Being an orthogonal matrix, it's invertible. Now you consider this S transpose Ux as the vector y. So now you
Okay,
get
sir, got it.
Vy is 0, that implies has to be 0. This is y.
Okay, thank you, sir. Got it.
Yeah, yeah. So this is how you solve. Now you want to find Ux equals to some scalar times E3. But you can see like the only possible way for this is X has to be E3. Otherwise it cannot work, right? Because of the structure of U. You can in fact solve this Ux equals to alpha E3 and then you will get X has to be also alpha E3. Hence the only solution, non-trivial solution for A transpose X equals to 0 is E3, which is your option number 3. Okay. I hope this should be clear, but if not, you can just go through the things that I said, then you will get it. Or you just solve this ux equals to E3, you solve this equation and you're done. Is it clear? If anyone has any doubt in this, they can ask. I can explain. Oh, some problem with
Yes, sir.
my earphone.
Yes, sir, you are audible. Please continue.
Okay, thank you. So let's go to next question. Question number 9. The rank of the matrix A is. Oh, okay. So basically, is this always true? Rank of A transpose is same as rank A.
Yes, sir.
Yes. Now we have observed that A transpose X equals to 0 if and only if, why I'm looking at this equation, because rank of A transpose is, see, A is a 3 cross 2 matrix, A transpose will be a 2 cross 3 matrix, means it is from R3 to R2, and in that case, the rank of A transpose will be 3 minus nullity of A transpose. Okay, you have to be careful, right? Because when when it is a square matrix n cross n, then you always know that nullity is n minus rank, or rank is n minus nullity. That's the same. But when you have rectangular matrices, you have to be careful where the domain lies, right? So now, what is the nullity? You have observed that nullity means the solutions of this equation A transpose X equals to 0. And you have observed this happens if and only if this happens, ux equals to alpha u3, and the only solution for this is x equals to e3. That means nullity is 1. So this kind of logic you have to build. You know how you will play with theorems or equations or the results that you got. That's how you get quicker in calculations for exams, competitive exams and all. The solution will be there. You can go either a long way, you can go finding the rank of the matrix A somehow. Even, it's not hard to find the rank. There are also
Sir,
other shortcuts that you find non-zero rows in the matrix S, that will be the rank, but you could try always to be innovative somehow, analytically.
sir, please repeat.
Okay, I'll repeat. Okay. So what we have observed is, see, A transpose X equals to 0 if and only if X is E3. Do you agree with this? We just have
Yes,
solved this. What does that mean? What is the nullity of A transpose? Correct?
Yes,
yes,
sir.
sir.
Yes. Plus, what will be the rank of A transpose? By the way, A transpose is a matrix which is 2 cross 3,
Yes,
which will be from R3 to R2 mapping. So it will be rank, it will be 3 minus nullity. Correct? And for any matrix A, rank of A is same as,
it transpose.
that's your answer.
Sir, what is rank of a matrix from, we can say, from S matrix that we have given, and that number of non-zeros? What you say?
Yeah,
Can you repeat?
the statement says that rank of a matrix A is same as number of non-zero rows in S. Whenever you write singular value decomposition of A as A equals to use S V transpose, the rank of matrix A is same as number of non-zero rows in S.
Only, sir, non-zero rows, or non-zero linearly dependent rows, independent
No,
rows?
no, no. See, it will have only linearly independent rows. Any non-zero row is linearly independent in S. That's how S is created. So we just count
Okay.
number of non-zero rows.
Okay, sir.
Yeah. Okay, so we are at question number 9. We are done. So question number 10. The condition number of matrix A is. What are the form? There is some direct formula, I guess, for condition number. If I remember correctly, that's the maximum singular value upon minimum singular value. Is it correct?
Yes. Yes, sir.
Yes.
Singular value or eigenvalue? Singular value, right? I use singular value.
Singular
Singular.
values.
Yeah, yeah.
Sigma 1 on sigma n.
So, okay, yeah. If you write the sigma is in this order,
Yes, sir. Greater than equals to.
then it will be sigma 1 by sigma n. Right. Oh, then it's just computational. You have to find singular values and then do it. Okay. Then the answer will be find A star A, the matrix whatever it is, and find their eigenvalues. Eigenvalues of A star A. B, I'll write in this format now in the decreasing order: sigma 1, sigma 2, blah blah blah, sigma n, and then the condition number is this, which will be simply sigma 1 by sigma n. That's the number. But as I don't know if this is correct, the condition number, is there any other crude formula in terms of like ax with x or something like this, inner product of ax with x and their infimum or supremum, something like this? Something like this is explained in the class?
No, sir.
Okay, okay. Maybe I'm confusing in something. But yeah, does anyone have any doubt there? G
Yes, sir.
Satvik?
Yes, sir.
Yeah.
Sir, what does condition number of any matrix tells? Geometrical interpretation of condition number. Can you say something?
Yeah, no, that's what I was about to recall. I'm sorry, this ill condition number I haven't read from long time. I
Okay.
don't
Okay.
remember, but as far as I know, this is just a consequence. This is not a definition. This result is a consequence, how you will find a condition number. But yeah, the nice interpretation, okay, I have to read and tell you. Maybe in the next session, I'll say. Okay, we have some topics for the
Okay.
next session.
Okay.
Some geometrical meaning. The condition number. So this relates to the ill-posed problems, right? Like if you want to solve Ax equals to B, and when the matrix is not invertible, then even certain changes in X will lead you different outputs. I mean, see, if Ax equals to B is the solution, and if you change X, you say X tilde is some X minus epsilon. Okay, I just subtracted some number from each entries. Then how much change you expect in B, right? I mean, the new B dash that you get, will it be like some neighborhood plus minus epsilon or something? Like what change you expect? In data analysis or such topics, you are interested in such things because data is not always fixed. There will be changes in some coordinates, some entries. So you allow entries to change with some epsilon, but you want to predict what's the outcome, right? So you need such matrices for which even if you change do some small changes in X, the resultant should not be so dynamic. So that you determine by the condition number of a matrix. If that number is small, then the matrix is kind of stable, and if it's large, then it's unstable. So roughly, this is the application or meaning I know, but I'll make it precise in the next session. Does it answer your question somehow?
Yes, sir. Got it.
Okay. So the question Madhavi R asked is how to find. Okay. How to find smallest singular value if I have the condition number and largest singular value. Then you can find, no, from this formula. Singular, if you have the condition number and if you have the largest singular value, then the smallest singular value will be just sigma max upon Ca. From this formula you can find.
Okay, sir.
Yeah. So if anyone has any doubts, they can ask. How to find j power n for Jordan block? That's what I was doing there. Multiplication. There is a simple formula as far as I know. I don't know, remember the formula exactly, but you can look for the formula. Jordan exponent or something you can search, or maybe it's there in the notes. Or yeah, sir might have explained it in the
registered mobile number say 08066982707.
yeah, sir might have explained that in uh, the videos, but if not, just let me know in next session. I'll see the formula. You can search for internet, you will get a formula for j power n. It's not so hidden. There any other doubt? Okay,
Sir,
so
is
yes,
there any
please.
is there any conclusion we can draw from minimal polynomial of any matrix, and that from this we can say about the Jordan canonical form of that matrix? Is there any relation between them or not?
Okay, so you want to determine kind of Jordan matrix from minimal polynomial, is it?
Yes, sir.
Yeah, just by a minimal polynomial, I don't think you can, because you from minimal polynomial only thing you will get is the are the degrees of the factor x minus lambda, right? If you have minimal polynomial, you get degrees of x minus lambda, right, for every lambda. But that from that you get the largest Jordan block
Okay.
in J. This is the only information. So it depends on the size of your matrix, right? So sometimes you get lucky, because if suppose matrix is 3 cross 3 and you get minimal polynomial x minus 2 cube as you got there before, then you know that the maximum Jordan block is of size 3 and there are the total number of Jordan blocks can only be 1, because the matrix size itself 3 cross 3. Then you can completely determine J. But in other cases, you can't say really.
Okay, sir.
If I add this up with geometric multiplicities, then I have something. Because then I know total number of Jordan blocks, and then I know the largest Jordan block. Yeah, but still there's a problem. Yeah. Like if I know that there are 4 total Jordan blocks, and if say largest block is of size 2, then what are the possibilities? Possibilities can be 2, this is, yeah, 4 total Jordan blocks, largest size 2. So it can be 2, 2, 2, 2, or like 2, I'm sorry, 2, 2 or 2, 1, 1, right? Is it? Yeah.